Now let me talk about feature vectors. Okay, and this is something that you will see in naive-based classifier. Fine. So this is important from that perspective. So I told you that I flattened this image out. So I got a 784, 1 cross 784 ka vector. The dimension of this particular vector is, dimension is it a 1D vector? Again, okay. 784, right? So this is a 784 dimensional vector, right? Similarly, so this is a 0. This is, I don't know, probably a 5. This is a 3, right? So these are feature vectors, right? So now pixel, every pixel is a feature. Every pixel. So these are pixel values, right? So this is pixel, this is pixel. Image has pixels if you don't know already. Pixel, right? Right. So this is a pixel, right? So these are pixels, right? So every pixel here is a feature. Okay, why I'm saying that? So yesterday we had seen a table of data, right? Uh, right. For example, we had seen price, number of floors, or I just say floors, bedrooms. So this was house price prediction data that we had seen earlier. Price prediction data, correct? So we had seen some these things, and like there were many features, right? So everything was a feature. Here, this was feature. This was the label which we wanted to predict in the regression problem. This was a feature, like how many floors are there. Bedroom was also feature. How many bedrooms are there, right? So these were features, right? And this was like a feature row, right? And this was one data point. Agreed? In the last lecture, we have seen this. This is one data point, correct? Right? In the last lecture, we have seen this. Even if you have not attended the last lecture, this is this is one data point, and this data point has some label and some features, right? Similarly, if I put all of these vectors in a table, will you say every row is still a feature for a particular image? It's not a feature, it's like a feature vector for a particular image. So what I will do is I'll just stack them together in a table, most likely. So this is pixel 1, pixel 2, this is pixel 3, and so on. And I have pixel 784, right? And let me say that these values are slightly different because they map to some different digits. This is 20, also this is 21, right? And the label is here, say 3, 0, 1, and 5, right? So if I have this table of data, how many features I have? How many features we have? Varshita, incorrect. How many features? Look at the table. This is one data point, right? This is one data point. How many data points we have? 4 data points. So we have 784 features, right? Can you see that every pixel is a feature now? Right? So we have 784 features here. Fine. Now this row is, right? This row is called a feature vector. This is the row of features, is nothing but a feature vector. It's called, right? This is very simple. Feature vector. It's a vector of features. Vectors we have seen in linear algebras in detail. Called feature vector. Right? So some terminology here. Right? What is the dimension of this feature vector? Actually, X is also, Y is also part of this feature vector. Okay. So this is feature, but sometimes we take the Xi and Yi together. Okay. So this is, if I take this, then it will be 785. If I just take X, it will be 784. Right. So why did I write label separately? So that you understand this is different data points. And this is the Yi. If you have seen the last lecture, this is the Yi and this is the Xi. Right? So this is X1, this is X2, subscript, X3, X4, right? And this is Y, Y. This is X1, X2, X3, X4, X784. So 784 features. Bhavish, your doubt is clear. I just wanted to show you that these are different images. These are corresponding to different images. And this is how this feature looks like. Okay. So this is the feature. Actually, row features plus label, I think. Plus label also is called the feature vector. Okay. So some terminology, but you understood that this is one row of data corresponding to one data point. Fine. So how many data points in this? Again, data points 4, right? 4 images are there. 4 flattened images I have put here. They correspond to this to 3015. And I have 4 data points. Fine. Everybody understood this. Okay. So we understood feature vector, correct? Awesome. Okay. Now let me go back to my simpler example, which I think people will understand better. So I have this cat data set. Okay. I have this cat data set where, I have like cat IDs. So this is cat 1, cat 2, cat 3, cat 4. So there are, what are the features here? How many features are there? So this is just an ID. It's not usually a feature. So this is not feature, right? And say, let's say this is my label. How many features are there now? So this is label. Oh, fine. So there are 3 features, right? I have X1, X2, and X3. Weight, age, and color are my features. Fine. In this particular data set. Now suppose that this is not label, right? And this is also a feature. This will become X4. Doesn't matter in what order I write it. It's X4. Fine. So there are 4 features I have, right? Now this is basically a feature vector. Along with the label, it will be a feature vector. Let's say this is unsupervised data, right? Unsupervised data. So label is not there. So only this will be the feature vector, or this is the feature vector. Correct? Okay. Okay, this should have cropped out. This cat ID is not required. So IDs are usually just to identify what data point is there. They're not part of the features, vectors. Fine. Okay, so breed is a feature. You understood, right? This is a feature. And there are around 70 cat breeds in the world. But we will only talk about the cat breeds that we have in our data, right? So how many cat breeds we have? Different cat breeds here. So we have Siamese, we have Maine Coon, we have Persian, we have Ragdoll, and we have domestic Shorthair. Okay, so we have 5 different varieties of cats. Okay. So why am I talking about, this particular feature? Because I want you to take to something known as joint probability distribution over feature vector. Even if you don't understand, that's fine. Fine. We'll get there. So, okay. Fine. So now I want to basically model the distribution of this breed, right? So this breed, so let's see this breed feature. Okay, so this is the breed. I'm telling you that there are 70 breeds in this whole world, but we are focusing on only seven, only five, sorry, only five, right? So there are breed one, breed two, breed three, and breed four, and breed five, right? So there are five breeds here, right? Now I want to understand the distribution of these breeds in my data. Why do I want to understand? So I want to analyze or model the distribution, analyze or model the distribution of breeds in my data. My data. Okay. So see, all the real world data is coming from somewhere, right? And these cat breeds, if I have to talk very specifically about, then these cat breeds have some inherent distribution, right? For example, suppose some breed is rare. I don't know which breed is rare. Say this particular breed, so you will see every day, right? This domestic short hair. I'm very sure that you guys have seen this color, this cat like this, right? This is a very common cat, right? So domestic short hair cat is very common, right? So suppose that if you have 100 samples, domestic short hair is like 50 of them, right? So 50% of your data has this particular breed, right? It means that this breed is very common, right? In the whole world, right? Now I want to actually talk about and I want to think about the distribution, original distribution of these cats, how they are in the world, right? I actually want to go there, but all I can do is whatever data I have, I can estimate things from there, right? For example, in my data, if I have 50 samples of domestic short hair, I will say that 50% of cat breeds is this domestic short hair, right? Similarly, other breeds maybe say 20%, 20%, right? And 5%, 5%. Or let me say this is 9%, this is just 1%. 1%, right? So this particular breed is just 1% of my data, right? So I have just one example of this breed. So this is a rare breed, right? This is very rare, right? Correct? Yes, no. At least according to my data, this is rare because I have just one data sample uh, for all the cats, right? So this is just one data sample out of 100, right? While this domestic short here had 50 samples. So they were like in abundance. So this is probably like a Sphinx cat that we had seen yesterday, right? So Sphinx cat, I have never seen a Sphinx cat in my life. So I'm assuming that is a rare breed. Fine, because I've never seen that. So this domestic short here, so we understood, right? So our data basically gives idea about distribution, right? Now this distribution, can I create a probability distribution from this? I have this data. Can I estimate the probability distribution? Yes, no. Can we estimate? We can, right? How will we do that? Suppose I have to estimate from these samples. What will be the PDF of this breed? What will it look like? Okay, I've already mentioned. Give me, say, points. So if I have to write the PDF of this, right? How will I write it? So I will write it like this. So this is the probability mass, right? So this is 0.5, this is 0.2, this is 0.2, this is 0.9, and this is 0.1, right? So now I have, sorry, this is probability mass function, sorry, not PDF, probability mass function, right? So this is probability mass, right? So this is, oh, sorry, this is 0.09, correct. Thanks. So you guys are alert. Good. Right? So this is right. Add this up. Is it 1? So this is a valid PMF. Correct? So PMF of breed I've got. I will write it here. If I do it like this is the PMF, right? We have estimated this PMF. This is not, might not be true. Like in real world, we don't know. There are 70 breeds. I can't get the data of all the breeds in the world. But whatever estimation I have, I can estimate a PMF, right? Now, can you say something about breed? What is breed? Breed is a random what? Can I say breed is a random variable from which my data is coming? If this follows this data distribution, can I say breed is a random variable? I can assume breed to be random variable, and the data that I am receiving is coming from the distribution of this breed random variable. Agreed? Yes. No. Yes. Correct? With this particular probability mass function. This is an estimate, right? I just want, this is an estimate that I did, but there is some original PMF that these cat breeds will have, right? I have no idea about that, but I would like to estimate it. I would like to estimate it because of multiple reasons. I'll come to that. Why would I want to estimate the probability mass function of this particular breed? Okay. So everybody clear here that a breed can be thought of, or a feature can be thought of as a random variable? Yes, very important point. Well, this is a very subtle point. A lot of people don't understand this, and then they don't understand data distributions, and they don't understand the mathematics uh, uh, behind the machine learning. Okay. Okay. Let me say that again. Okay. So I want to, so my original goal I'll give you, I wanted an estimate, or I want to learn the distribution of these breeds in the world, right? But I can't do that. But I am estimating that using this data, right? Also, another thing is, can we think of every feature as a random variable? This breed is one of the features, right? I can do the same thing for every feature that I have, and I can look at their distributions in my data currently. Let's forget about the world, right? In my distribution or my data, at least I can get an estimate. Like, what is their PMF looking like? Correct? So every feature, can I say that every feature is a random variable? Every feature is a random variable. Or you can assume it to be a random variable, right? I can always think, you can always think like this, that, oh, breed is coming from some distribution. I don't know what distribution is that, but let me estimate that, right? So if breed is coming from some distribution, it means that breed is a random variable, right? And whatever samples I'm getting is basically that sampling from that PMF, right? It's basically the samples that I'm getting, or realization of that PMF. I don't know if you guys were introduced to this term, realization and probability. So this is called realization of PMF. Support or realization, correct? Right? So basically, support or realization of a PMF is that you have a probability mass function. You're just sampling data from it, right? So if I sample from this particular probability mass function, do you agree that I'm more likely to get samples which belong to this domestic short hair breed, B1 breed, because the probability mass is higher for this particular breed? Yes, no, right? Bhavesh, is it clear to you? Bhavesh, Anirudh, have you guys studied probability as of now, or random variable? Okay, so is this making sense? Okay, Bhavesh. So just go through random variable. What is a random variable in the probability course? You'll understand this. Uh, but at least I posted a message yesterday that you should know random variable before this lecture. Okay, no worries. Whenever you study random variable, come back to this lecture and then understand. Fine. Uh, so, Bhavesh, if you don't know random variable, just know that there is some distribution from this data is coming, right? And you can assume that data that you have received, on which you are working right now, for example, this data set that I received, right? What I have done is, this probably, this was like a probability mass function. uh, uh, or some distribution from it was coming. I have just realized that I've just taken samples from that probability function. Okay. So because domestic short here has a probability of 0.5 of occurring, so I'm more likely to get DSH samples in my data set. Till this makes sense? Right? Okay, fine. Okay. Now, the question that you should ask me, that why do you want to model the distribution, right? Why are you thinking about data in terms data and distributions altogether, right? So actually, data modeling the data distribution, right, is very fundamental part of machine learning. It's very crucial, and you will see once you learn a little advanced machine learning, you will understand that everything that we do is basically modeling data distributions, right? What we try to do is we want to replicate the distribution of the data from where it's coming. And if we are able to replicate the distribution, right, we have won. If we are able to distribute, if we are able to for example, know the distribution of cancer patients in the world, right? If I can know the patient, like the distribution by which probably nature or universe is giving us the cancer patients, if I know this, I think we'll be able to crack the cancer problem. Or it's like you will know that okay, what person can have cancer, or how the cancer is going to grow, so you can take certain measures. Probably cancer is not the best example, but let's say cat breeds, for example, as we were talking about, right? If you know all the cat breeds, all the distribution, right, then you know every data point of that particular data, right? Then you can build, or using that particular distribution of data, you can build a machine learning model that will be like 100% accurate always. Once you know the data distribution, right, you know everything about that data. You don't even have to build a machine learning model. You can only have the data distribution, and you can go back to the data distribution and look at that, and uh, predict everything about that particular data, right? So data, you will see that modeling a data distribution is a very crucial thing that we do in machine learning. We might not be doing a lot of data modeling in this particular course, but if you do probabilistic machine learning, you will see that it's just data modeling. It's just modeling how my data is, what from what distribution this data must be coming. Let me try to replicate that data distribution. If I'm able to do it very precisely, very well, I have a very good algorithm. Okay, so it's a very crucial part of machine learning. We always want to model the data distribution. Right. But again, I want to add that point that we don't know the actual distribution, because if we knew the oracle is something that, I don't know if you guys have heard this term. Oracle is something that knows everything, right? So if I have the data distribution, right, I can build this oracle which will know everything, right? But the thing is, we never know the actual distribution. We can only do the estimation of that. So Rohini, you are correct. We will never know the actual distribution of the data in this whole world. We can only do some estimate, and that's what we do, right? We always, whatever machine learning model that we are building, right, is you will see eventually that they are just estimating the data distribution. They are just seeing that, oh, this is the probability of getting this data, and they're just going with that. Most of the machine learning is that. So that's a very different perspective. Spend some time. So this is not very clear to everyone in the first go. This is not clear to me when I first understood this. So think about it for a very long time. By the end of this machine learning, I'm hoping that you will understand that whatever we do, we actually just model the data. Okay. So even if you don't understand it, as the course matures, I'm pretty sure you will understand that whatever algorithm we are using is just modeling data distribution. Okay. And modeling data distribution is very important because you can do a lot of things. You can do analysis, you can do predictions, you can make decisions in various fields based on modeling the data distribution. Fine. And sometimes, we make assumptions about this data, whatever data is, right? For example, this cat breed, right? So I'm assuming there are only 5 cats right now if I have to build a model. But suppose that next time I build a classifier for these cats into these 5 classes, and I see a new class of uh, of cat, a new breed of cat, right? Then my model will not work, right? So I have to go ahead with some assumptions, because I will never be able to get all the 70, 80 breeds that are there in the cat. I will never be able to get the whole data of it, right? Or unless I spend too much money or too much time in collecting all that data, I will not be able to achieve it, right? So we actually, whenever we are doing machine learning modeling, right, whenever we are building models, we are actually making some assumptions of the data. For example, in naive class, if you have in naive based classifier, you will see that we assume that every feature is independent to each other, right? So we have to make some assumptions about the data so that we can apply certain algorithms. And whenever you see a machine learning algorithm, your first question should be, what are my data assumptions? What am I assuming about the data so that this machine learning algorithm will work, right? And suppose that your data does not adhere to those assumptions, pretty sure your machine learning algorithm is not going to work well, right? So every machine learning algorithm that you'll see will come with some inherent data assumption, and only if your data abides to that data assumption, then your machine learning algorithm will work. Otherwise, it will not work. Fine. These things will become clear as we go on. Fine. Another 3 points, right? So data that we receive right now is not very diverse. Diverse means it doesn't capture everything, right? Suppose I go and collect data about cats today, right? I might be only able to collect data in Bangalore, where I'm sitting right now, right? Suppose I spend a little more money, I might be able to get the data of the cats in Karnataka. Suppose I spend more money, I will be able to get the data for India, right? But again, if I have to get all the data of the world, right? If I'm building a cat classifier, I should be able to handle all the cats that are there in the world, right? That are there in the world, right? So I will have to spend a lot of money. I probably have to be like Elon Musk or Jeff Bezos to spend that kind of a money to collect that kind of a data, right? Even Amazon and Tesla and other Google don't have all that data, right? And these are such tech giants, right? They have been collecting data for years, right? Google has been collecting data for years, right? Image sub, just imagine the number of images that are uploaded in Google Photos right now. So even then, I believe that Google will not have all the categories, right? So if Google cannot do it, for me as a single individual with not enough money as Google, I don't think I'll be able to ever collect that kind of a data, right? So the data that I will be able to collect will not be that diverse. And only when you have a lot of diversity in your data, you actually build better models. But because data is not diverse, I'll have to make certain assumptions about the data. For example, I will make assumption that, okay, the classifier that I'm going to build for this cat data will only predict these 5 classes or these 5 breeds, right? And I don't know any other breed from these 5 breeds. So that's one data assumption that I'm making, right? And hence my model will only work for these 5 breeds. It will not work for the other breeds, but because my model has never seen them, right? So the data is not diverse, and it's very difficult to get diverse data. Hence we try to model the original distribution. Sometimes I say, okay, maybe I'm not able to get the real data, but can I make some assumptions about the the data distribution? If I'm able to do that, well and good. Whatever best I can do, I will try to do that. Fine. Another thing, insufficient data, same thing, right? So there are, I don't know, millions, billions of cats. I don't know how many are there. But if I start collecting data about every cat in the world, do you think I will get all the data? I will not get all the data, right? And in my capacity, I think I will not be able to get more than, say, 10,000 images of cat, right? So whenever I'm trying to build this classifier for cat, I think I will never have data. And there is one principle of machine learning algorithms. The more the data, the better the model. Okay. So as much as data you can have, you should put it. Uh, and if you don't have enough data, your machine learning model doesn't work well, right? So there is a principle, more the data, better the model. Better the model. Right? So suppose I'm building a cat classifier, right? I will never have enough data for my model because it will never see, diversity is not there. I will not have enough samples. The breeds which are rare, I'll not have enough samples for them. So my machine learning model might not learn those rare breeds, right? So I will always have insufficient data, and mostly you will have insufficient data, right? Other thing is noise and outliers, right? So a lot of noise get introduced in the data collection process. For example, some sensor that you're using for collecting the data, right? Now, if the sensor goes bad, right? So there'll be a lot of noise introduced, a lot of outliers, we call it, will be introduced in your data, right? So if you can model the distribution of the data, and if you know exact model of your data distribution, you will know what is noise, what is outlier, right? Suppose, for example, uh, I have marks, right? I have marks. So marks can range from 0 to 100 only, right? Suppose I'm taking some exam. So my marks can range only from 0 to 100, right? Let me, okay. So this is my, say, study hours, and these are marks, right? So they are linearly correlated. Correlation is basically how they are related to each other. So you will see that as you increase your study marks, your study hours, your marks will increase, right? So this is the distribution that you will usually see with the marks, right? Now this is 100 marks, right? Suppose one point is here, which is like here, right? 101 mark in your data, right? So I know that my marks cannot exceed 100 marks. So this is an outlier, right? This is noise in my data because my marks can never exceed 100, right? So this is an outlier. This is not part of the data. I should probably remove this data point. Otherwise, my model will not learn well, right? So if you know the data distribution, I knew that these marks can only be from 0 to 100, right? Hence, I'm able to detect this outlier. Had I not known this range, I would have gone ahead with this outlier and my model would have, so instead of predicting, having a classifier predict like this, my model might have been predicting like this, right? So I will not get the real estimate of the data if outliers are present. And how will you know the outliers are present? You will have to model the data. Okay. So another is asking that is there a workaround for insufficient data to build a model as of date? So the workarounds are there. You can actually generate uh, synthetic data. Okay. There are many things that you can do. You can generate synthetic data. Basically, you generate data and you use generative modeling for this. For this also, you'll have to model the original distribution of the data as best you can do, and you will take samples from that. Okay, so you'll do generative modeling from which you can generate the data. You can do something very famous technique, augmentation. So whatever samples that you have already, you will add slight noise to them and add it back to your data set. Fine. So there are methods, but nothing is very short. Not everything works every time, right? So you will have to try a multiple technique, a lot of techniques, and see. Fine. So coming back to the slide, why do we want to model the distribution? If I know the distribution of the data from where it is coming, it is easier for me to detect the noise and the outliers and to eliminate them. And the better the quality of the data, the better your model is always. Okay. So this is another thing. Better the quality quality of data, better the model. And as I've seen, if your data is labeled accurately, right, your model will do very well. But if you have noise in your data, your models don't learn that well. Fine. Okay. Uh, should remove. Fine. So, okay. So this is another. Uh, these are five breeds actually. So the thing that I already have mentioned. So there are five breeds, and I have taken a different distribution of the data over here. So this is zero point 0.4, zero point 0.2, zero point 1, zero point 0.2. Let's see, this is the probability distribution of cat, right? And we saw that cat breed is a random variable. So now if somebody says to you that every feature is a random variable, will you agree? Right? So you'll not be confused that every feature is a random variable, correct? Fine. Okay. Very happy about that, right? Every feature is a random variable. Very big announcement. Like, it's like a lot of people don't understand this, that you just don't look at the data that you're seeing on your screen. You have to think about where this data is coming from, right? And to do that kind of modeling, you use probability and statistics, right? So hence probability and statistics is very useful for machine learning. And same thing goes for linear algebra as well, right? You see that matrices and vectors are coming in when we are talking about machine learning. Hence, you should study linear algebra and probability with a lot of depth so that you can master machine learning. Fine. So we have understood every feature is a random variable. Very good. Now I want to argue something. So this is something that you will see in knife-based classifier. I want to say that every feature vector is just a joint probability distribution of random variables. Okay. Now that you have understood that a feature is a random variable, now can you think about this, that I can model every feature vector? So what was my feature vector? Feature vector was this, like feature 1, x1, x2, x3, x4, right? Something like that, x5, right? So this feature vector is nothing but it's coming from a joint probability distribution of random variables, right? How do these random variables are interacting with each other? It's coming from there. Like, it's a joint probability distribution of these random variables. If it's not clear, it'll be clear now. Fine. Okay. So I'm changing the data a little bit. I'm introducing one more color so that I can show you that it's a joint distribution always, right? So I'm talking about breed and color right now. Okay. So for example, in Siamese cat, you will see white color as well. In Maine Coon, you will see brown. Persian cat, the color is black. Ragdoll is gray. Domestic short hair also has an orange color. Siamese also has brown, and all of this, right? Now let's try to model the distribution of this particular data. Okay, so this is the distribution. Can I compute the joint probability of these two vectors or these two features? Yes, no, joint probability. Joint probability is like nothing but how many samples are there for both of these, or how many samples are there for example, Siamese and brown, right? So we can create that. So for every breed and every color, I will count the number of samples, right? So for example, Siamese and white, I have only one sample, right? One sample here. Siamese is here, Siamese is here. I am seeing only one sample in white. So this is, and how many samples I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 samples I have. So out of 10 samples, I only have one white colored Siamese, right? Another color of Siamese is brown, right? So I have one more cat which is brown color and is of Siamese breed, right? So I can populate this whole table. Yes, no, right? What is this? If I take now these are, what are these? Okay, tell me all. What is this? These values. 2 by 10, 2 by 10, 2 by 2, 2 by 10. These are marginal probabilities, right? Right? And we are calculating the joint probability distribution of these two breeds. Oh, sorry, these two random variables. Agreed? Right. Okay. So this is a joint probability distribution, right? So now suppose I say, what is the probability of having cat X is equals to Siamese and color is equals to say black. What is the probability? I will go to Siamese. I will see black. Oh, this is 0, right? So this is 0. Let's do more. So this is 0, right? So X is equals to Siamese. Let me take some other breed. Let's say ragdoll. So I'll say ragdoll breed. And what is the probability of having X is equals to ragdoll and color is equals to say gray? 1 by 10, right? 1 by 10, 0 probability, right? So what I have done, I have estimated the joint probability of these two breeds, right? Now, suppose that the data that I have had is very close to the original world data, right? My distributions or my these probabilities will be very accurate, correct? Right? Now, suppose I see one example, or say I see 5 examples of Siamese cat with black color. Right? And assuming that this data is actually world data. Actual world data. So whatever joint probability that you're calculating is actually very close to the original distribution. And suppose you see 5 samples of, like later, whenever you're doing something, you see these 5 Siamese cats with black color, right? So you will immediately know that this is some noise or outlier, right? Because you're saying that I've estimated the original probability distribution of my cats and their breed and the color, but I'm seeing the Siamese cat with black color. So something is wrong because that's not matching my original distribution, right? Or you will take actions regarding that later on. But did you understood? Did you understand that you can actually model these two features together and you will get a joint probability distribution? Now, if somebody says that feature vector is nothing but a joint probability distribution of random variables, will you agree or not? Right? Fine. Okay. Yeah, so this we know that joint probability is calculated by dividing the count of each breed and color combination by the total number of observations. This is what we did. And you guys are expert in doing this. Fine. So we calculated. Yeah, so Vashita is asking if there is just one feature, we'll not have a joint probability distribution, right? Yeah, so once you have more than one random variable, then you have a joint probability distribution. Otherwise, you don't have joint probability distribution, right? Okay, so now you have understood that every feature vector comes from a joint probability distribution of random variables, right? Because I can assume there is a inherent distribution behind these features, a joint distribution behind these features. So, or these random variables. So they're coming. So every row that you see in your data is actually coming from some joint distribution of these random variables. And these random variables are nothing but features, right? And sometimes we have to make some assumption of this distribution, right? Not sometimes, I think 99.999% times, you will always assume this distribution. You will not know that there is a distribution like this or what is the original distribution that is coming from, right? So in real world examples, you will not know the original distribution. So you'll have to make some assumptions of the distribution and work ahead. Fine. So I'll just reiterate on what we were discussing. So Rohan was saying that technically, you know, a random variable has to be a number, like this value should be a number. Technically, numerically, that's right. But you can have categories here and you can actually compute the joint probabilities. You might not be able to do things like probability of x less than 1, right? These kind of things, but we are not interested in those kind of values. We are only interested in knowing that, suppose I'm getting one example like this, where I have, for example, this. There's a data set. Here is a data set, right? Suppose I get this sample in my data, and I already have created a data distribution for myself. I have already modeled the data distribution myself. I will just check whether this particular sample, how likely this was supposed to occur. And the right now, the estimated probability that I'm seeing, the estimated joint probability of this particular feature vector that I'm seeing, is it mapping to my original distribution? Because if it doesn't, that it means that something is wrong with the data and I might have to correct the data. I might have to do outlier detection and things like that, right? So data distribution is very important. And sometimes we map data distribution, we model the data distributions. We try to understand how the data is, like what is rare, what is not rare, and things like that. Also, they're helpful, in deciding what model to use. Okay. So suppose that you know the data distribution. For example, I was giving you the example of marks, right? That if I have this marks card data set, I don't know where I put it here, right? So if I had this marks data set, right, that your marks will improve with the number of study hours that you put in generally. But if I had already known that whatever I have been plotted here is marks, then the marks can never cross. I cannot have a data point which is crossing y is equals to 100, right? Because my marks cannot exceed 100 marks, right? So I knew, because I knew the data distribution, I knew that this kind of a problem is there. Apart from this, it also helps if you understand the distribution of the data, you also are able to understand what model to use, right? For example, suppose you want to use regression algorithm here, right? So let me build a little base for you here. Suppose that this is some data set that has been given to you, and you're seeing that, okay, there is a feature called age and there is a feature called bone density. And you can see that with age, as your age increases, your density decreases, right? So you can, so regression has, multiple types. You will have a linear regression where you will fit a linear line to it. Line is fitted to the data, right? Then there is like a polynomial regression where you fit a polynomial to it, to the data. Polynomial. Polynomial, right? You can put a polynomial, right? But on the basis of this data, if I visualize this data before, I will see that there's a linear relationship kind of a thing. Obviously, the data is not exactly on one line, but it's very close, right? So even if I fit a model like this, right? If I take this linear line to be my model, right? And whenever I, for example, get some bone density, I will predict the point here, right? If I get bone density here, suppose I get the bone density to be something here, then using this line, I'll predict this point, right? I'll predict this. So this is my, say, x1. So this is x, sorry. This is, say, sample one. This is sample two. And this is my, basically the prediction for y cap. I don't know, I'll say cap. It's basically used for prediction. So this is for one and this is for two. So what I'm only doing is, you'll see this in linear regression, how you fit the line. But you can see that instead of having like a model which goes over every sample, you have a very simple model, which is a linear line like this. And you're basically predicting points or whatever value that you get for bone density here. Okay, for example, the feature that you have is bone density. And the label you have is, I should have said this before, is age, right? So suppose I get the bone density of some patient, which is here, right? And I have already fitted a line which very aptly represents my data, existing data. Then I can predict that, okay, because the bone density is very high, so this patient is more likely a young patient, right? So this is y cap 3, the prediction, right? So you'll see this in linear regression, but just seeing the data, you can actually decide what model to use, right? You don't even have to go to more complex models like deep learning models and neural networks if your data is this simple, right? On the other hand, if you have a data like this, right, and you say that I will use a linear predictor for this, right? So what it's saying is that you have age, or say your feature is, say, memory, right? And your label is, say, age, right? So suppose your memory is here, right? So you don't know, right? You can't predict what will be your age. Your age can be in this region, your age can be in this region also, correct? So probably if I try to fit a linear model here, it will not work, right? You can see that a lot of points are off this linear line. Hence, a linear model will not be a good fit, right? A linear model is not a good fit. How did I know this? because I plotted this data and I visualize it that the memory and the age doesn't have a linear kind of a relationship. So I can't have a linear regression kind of a model going on here. Good fit here, right? So if you know the data distribution of you, even if you plot this, right, you will get to know a lot of insights about what kind of model you should be using. For example, here, maybe you would want to fit a parabola kind of a, not a parabola, yeah, a shifted parabola kind of a thing, right? You might want to fit that rather than a linear model. So visualizing the data helps us a lot understanding what model to use. And also, if I had known the original distribution of the data, right? If I had the original distribution of the data, I will know exactly what kind of a model will give me the best results, right? So hence modeling data distribution is very important. Also, if you know the data distribution, it becomes simpler for you to decide your modeling, like what will be your modeling choice, what kind of models will you use, right? You will see this further in the course, but just to give you a gist that how the data helps us in determining what kind of model one should be using. Fine. Understood? Very simple construct. Nothing very fancy here. Fine. Okay. Now, again, I will just stress on this that why knowing the data distribution is important. If you already know the data distribution, I already talked about it, that you can do outlier detection. You can remove the data points which are essentially noise for your data. And the better your quality of data will be, the better your model will be. And this I have seen empirically. As you improve your data distribution, like the data labeling, not the distribution, the labeling of the data, as accurate as you can your data labeling, as good your model will perform. Okay, and I've seen this brings a lot of difference in your model performance. And just few mislabeled samples you remove from your data, you'll see a boost in your performance, right? So labeling the data correctly is also one other aspect of machine learning. Fine. So knowing data distributions are very important, and you should always think about whenever you're starting a machine learning algorithm, right? You actually spend a lot of time understanding the data first, right? First of all, you cannot have the domain expertise, so you will try to get that. Then, even if you have the domain expertise, right, it's not very simple all the time. So you have to gain a lot of insights from the data first. Then only you are able to build a good model. So a lot of time for a data scientist goes in analyzing the data, removing the unnecessary data, something called as feature engineering that can be done using dimension reduction. Also, I'll talk about it later. So a lot of time for a data scientist actually goes in processing the data. Model building is actually the very smallest part of a model building pipeline. Major time you will see is in data processing, and that is true for industry. At least that you will spend, like, I think more than 70% of the time cleaning your data and building ready, like prepping up your data for model generations, right? So very important to look into the data distributions, data, analyzing the data, getting insights from the data. So you should not shy away from that. Obviously, we'll not be seeing the techniques to clean the data and all that in this course, but you should always go and learn those techniques. Those are really helpful. Fine. Okay. Also, if you know the model, the original data distribution, right? You can do generative modeling. And this, like modeling the data distribution, right, is actually the generative AI that you're seeing right now. So if you know the original distribution from where the data is coming from, I think somebody asked that whenever we don't have diverse data, what can we do? In that case, if you know the data distribution, you can generate synthetic data and you can add it to your training samples and you can build better models, right? So something that generative learning is getting like on peak right now. So something that uses this learning the data distributions, right? Okay. Now let me talk about model parameters. Okay. So what are model parameters? Let me take an example from here. So this is, suppose, a linear model that I fitted. If you don't understand linear model, it's fine. You can come back to this lecture. So what is a model parameter? Okay. So I have fitted this line to this data, right? So now this data is basically telling me that the X, this bone density, and age have a linear relationship. And age are linearly related. Agreed? Right? I can also write an equation for this if I can. Okay, so probably not, but it will be something like this. Okay, so it will, I'm just writing a linear equation here. So I'll say that some, yeah, some equation. So it can be some bone density plus, say, A times bone density plus B times age is equals to some, is equals to some C, right? I can write it like this. A times bone density into B times age is equals to some C, right? So what is this A, B, and C, right? So this A and A, B, C are model parameters. And this is something that you learn using the data. So whenever that training phase was happening in supervised learning, right? You were learning what is this A, B, and C. So these are model parameters. You learn them via training. The model learned during training. Learn during model training. Right? And once you have trained the model, they remain fixed. Right? So now you understand the difference between a feature, an attribute, attribute and feature are the same, and a parameter. Features are basically the attributes of your data, right? The properties of your data. Parameters are property of your model that you learn while doing the training.